Okay, that's fine, that's fine.
Okay, so my final part of this course here is around mixed language programming, and that is something I have been doing quite extensively, both. Sorry?
Oh, I just wanted to check that there was sound.
Yeah.
Good, thank you.
Okay, so I've done a lot of mixed language programming, Python Fortran, C++ Fortran, also Pascal Fortran, which is also, there are development environments on Windows, for example, Pascal. And sometimes you need to combine languages. So Fortran, you can't do everything in Fortran, even if you wanted to, but there is a lot of things that it's not well suited for. So for example, if you want to do user interfaces or other types of things around it, you need to look at other languages. It could be that you have a Fortran code that you want to integrate in a larger framework. Then you need to combine different languages again. So for example, instead of spawning a Fortran code as a binary and running it separately, you can actually link together the Fortran code with the C++ code. And before the modern versions of Fortran, it was quite complicated to mix C++ and Fortran because of different calling convention and also not exactly knowing the data types that correspond between the different languages. So in Fortran 2003, there was a module added called I2C binding that provides all the C data types as a constant that you can use to declare variables in Fortran. Another thing that was also introduced was the value attribute for variables, for dummy variables, dummy attributes in subroutines and functions. And the value attribute corresponds to the C convention of passing scalars as by value. In Fortran, everything is passed by reference by default, but in C, scalars are passed by value. And that is something that can make it hard to call a C routine from Fortran without that, having that way of expressing the subroutine interface in Fortran code. So I will do two things. I will first do calling C++ from Fortran, and then I will do go through a larger example which does the opposite, calling Fortran from C++. But that will be a separate live code thing. So how do you call C++ from Fortran? So the general flow is that you define a header file and the C++ implementation file of your interface that you want to interface with. And in the header file you declare the functions in something called an external C clause that determines that these are external routines that you export in a certain way. And then in Fortran, you define the interfaces of this routine in interface sections. And you also take advantage of the I2C binding module to make the interface consistent between the languages. So I will start with the simplest functions that you can do. So no parameters, no return values. And if you look at the left side here, let's see if I can get a pointer. On the left side here, this is the header file for my C++ code. So I see you have surrounded my C++ function using this extern C declaration here. And then I have a CPP file that includes this header file. And here I have my normal C++ stuff here, like my IOStream and my CMath, so I can print out. So in this case, I just print out standard cout hello from C++. So this is what the first thing. And this is the easiest way because there is you don't have to think too much about calling conventions. So in Fortran, yeah?
Just a simple question. This is all C and C++. Here's no Fortran.
No, this is just pure C, or C++ in this case, but it could be C, it's the same. So I haven't gone into Fortran yet.
Yeah, but you don't need to modify your C stuff in any way because you want to call it from Fortran.
I would recommend doing this in a separate header file, this part here, but this here you don't have to modify, it's the same syntax as C++. And then,
One question.
sorry?
Do you have any specific case where you should call C and C++ in Fortran?
I didn't understand the question.
So some example where would you need to call C, C++ from Fortran? The library.
So yeah, typically if you write a library, typically do not rewrite. If you want that callable from C and Fortran, you implement it in one language, and then you just provide interfaces to the code from the other. So most MPI libraries, for instance, are these days developed in C or C++, but they are widely used in Fortran.
So this is a kind of reversed example. It's not, this direction is probably not the most common one, but you go from call C++ from Fortran.
It's very
Yeah, for MPI library, exactly, yeah, that's true. That's a very common example, yes.
Or glass libraries, many glass libraries are these days written in C.
Yeah, that's, so the next step is that you have to go into Fortran. I will always do that. I put this I2C binding directly here. Then you create an interface section here. Basically, you tell them this is a routine. I'm expecting a routine to look in a certain way. Then you do subroutine simple. This is the name of my C++ function. And here comes the extra stuff here. So bind C that tells Fortran that we are calling what calling convention to expect. So in this case, C. And then this is the name of my C++ routine. So that corresponds to the name when I compile. So it's the binding name, not the symbol here. And subroutine. And then it's just a question of compiling all these files together, compiling the Fortran code separately and the C, and then linking together. And then you just call it like this. So it's nothing magical. And then you get your C++ output. So now I will go through some of the different scenarios you can have. So we start with the easy stuff. We have two scalar parameters coming in. So you see these are coming in as values. They are passed by value, not by reference. I'll just print them out here. And in Fortran, you need to. So here I have A and B. Same thing here. Name easy, but it's in the C++ file. So this is C++. This is Fortran. And here I need to specify this I2C binding in my interface here. And then what this does here, that provides you with all the types that are available for C that you can declare. So here I can declare, so the first parameter is an int. I just do integer C int. And because this is not a reference, I have value here. So this argument here is by value. This argument is also by value. And that's it. Then I can call it like this, call EC2, 4. And you see here, it goes in there and prints out incoming values.
So what you have here, if you do call EC2, the 2 is a default integer, it's not the C int, so there's implied a cast, or there may be a cast if the Fortran integer doesn't match on a C int.
Good question. I think it will do a cast somehow.
Because the plain 2 is a default integer constant.
Yeah. But I'm not sure. Isn't that the C int as well?
It happens to be.
Yeah. But
so if you take a GCC compiler, it typically happens to be. But in principle, if it's not, with all these gymnastics here, you're providing the Fortran compiler with information it needs to have in order to insert a cast.
Yes, that's probably what's happening. You could also, you could have added a suffix here, underscore C, underscore int, to be really explicit that this is actually a C int. Then you avoid the cost, but then the code looks really horrible. But yeah, so this is by value, so no references. Next part is, okay, so we have a return parameter that's going out from the function. So in this case, we have just a pointer to a floating variable. So now we have floating point here as well. And then I do star C equals A plus B. So that assigns the value of C, the sum here. So that goes out as a pointer. This is actually the default for Fortran. So in this case here, I have A, B, and C. I have C float here for the floating point variables. I have, those are value. And then I have intent out. I could have left that out as well. C float, C, just like a normal Fortran declaration. And now I can specify here, it probably calls there as well, but 2, 4, those go in by value. And I have a C1 here that is a floating point. I have the code, I declare them as C float. So this is a C float. And it goes in here, I print out from here, this is a C equals to 6. So you see it comes in here and the sums it and it returns it out again. This is printed on Fortran.
Does it link if you declare C1 as real?
Let's see. C2. You mean it's not very nice.
No, real is real.
Yeah.
But does it give you a type description?
Let's see. No, it works. Let's see, we run it as well. Let's see if it gives some strange values. It worked. So somehow it figured out.
So in principle, you're providing it with all the information it needs, that it, if required, it could do it.
Yeah.
And this might be just a coincidence because we are happy with the compiler. No, it wouldn't be the case in all cases.
No.
But it's also problematic if C float is something different from a 4-byte real. Normally it isn't. But if that were to be the case, then it will be conversion for every time you use this, and that will hamper performance. So you need to be sure that there is no conversion going on, and this is also implementation dependent.
Yeah.
You don't know if it works nicely or not in any computer. So this is portable, but not performance portable.
It depends on if you have, so in this case I have the same version of the compiler though. So I have a C++ with the same, it's the same GCC compiler version of it. So
then it's no problem.
yeah, exactly. But if you have,
But then to begin with, you shouldn't have such a simple thing as Z in a subroutine. Unless you're using relying on inlining by the compiler.
Yeah.
Because the call overheads are tremendous for something like A plus B.
yeah, and I know that that's a trivial example.
If the routine has a decent body, then it is not, it's not a problem.
Or if you call it millions of times, that's also a problem.
But if each call then lasts 5 minutes,
Then it
that
doesn't
is what I
matter.
meant is a decent body. If the subroutine has a decent code body and spends a lot of time, the extra overhead for a cast is negligible. But in the first place, what you're always worried about is portability. That nobody wants fast garbage. Then if you really spend a lot of time on that machine with that compiler, you might go into profiling and see that's
I mean, it's also correct. I mean, passing by value is also slower. So this is just, I mean, if you can design your C++ things in any way, you can have references also.
But the simple number, it doesn't take much time to send over. So if it's low or not, doesn't matter. But if it's a large
Yeah.
If it's a structure, then you need to send the address.
Yeah.
And C also do that. So
And then you also have a problem how to define a structure in a platform independently.
I
So
have
now we-
a
yeah.
row and column header, yeah.
Yeah.
This is also a problem.
Yeah.
Can you compute on the Fortran side with the type C float?
So,
You said real C float there,
yeah.
which means that it will find the type which matches what the companion C compiler uses.
Yeah.
Now, could you, on the Fortran side, just do lots of arithmetic on the real C float data type? Is it like?
Yeah, I did that in the actual code here.
That's what you had in first.
So I have declared all my variables as using C float to make sure that they are the same.
But somewhere then in that routine, you must have this stuff that is with the use of a C ISO binding on, because otherwise it will know what a C float is. Can you?
Yeah, it's sorry, it's at the top here, ISO C binding. Otherwise, I mean, before when I did this, before we have, you just kind of try to figure out what matched. And that's even more dangerous because it could change. And
Yeah.
In principle, C and C++ has not defined precisely what float or int or anything is.
no,
Same for Fortran. I've worked on a lot of machines in the past where default real was 8 byte. The case of the 90s, they had default real was a double precision. There was no difference between real and double precision.
Well, a friend of mine said that he said that if you did double precision, it did double precision, but in software. So a double precision was 128.
okay.
There's quadruple. I think the YMPs they had a double precision and real was the same.
So you mean to be sure I've written a program for variables to check out this, so to be sure that I know what's going on.
Yeah.
But if you go on a smaller scale, I mean today we go from the edge to the supercomputer. If you are going on a smaller system, it's dependent from card to card on the embedded market what a real and a double is. Sometimes they report 4 bytes each. So, and even a long could be 4 bytes and so on. So you really have to make sure that you know what you're doing.
Yeah, and you probably have to have a Fortran compiler for that small platform as well to be able to.
You can, a very simple computer can run Fortran and GCC, so
Yeah. And hopefully those bindings are also adapted downwards. So if you have a C int, it's But this is the best we can do somehow. I would say it's.
But normally we run on big system where you have sysadmin that can help us, so
Yeah.
to get the software up and running.
So there is another way. I mean, I don't really like this in C. This thing here. You can do the same thing works with this example here. So when I do C++, I usually do this if I want to pass out float and C. And then you can do C equals A plus B. And that works here as well. So it's the same declaration. And that looks nicer in C at least.
Isn't it?
Huh?
It was first in C++.
No, it's C, C++, it doesn't matter, but
I think C99 didn't have.
which
So it was, the ampersand was later in C than in C++.
okay, you're probably better in C than my.
I remember that at some point I was very upset. I thought that was cool.
Yeah, I'm C++, and I think this one looks nice. No, this one looks better. At least in the C++ code, you can. This is a standard declaration in C++. You have and for going out. And that works nice to this as well. So to the grid, so now we're talking arrays instead. This is not the most efficient code, so please don't hang me for the loops. But I have 4 arrays coming in here, A, B, C, and I will add C here. And this is by reference everything, so there is nothing special we have to do. I pass the N here because I need to know the size. And then I have A, B, C, N, and I have just C floats A star arrays. And I pass value, the n by value. And then in Fortran, I declare it like this, just like normal, allocate, and call my arrays over here, pass the 20 over, and it works.
Can I put the n as a star? So quite often what I like doing is that instead of having a star, I put the n into the brackets. Does that work or does that upset me?
You can try.
If I do Fortran, it works.
We can try. I think it works. I'm sure if I have to have this. You can try. Yes. And I think it runs as well. Yes, it works. Also functions. This is a C++ function or C function. Returns sign of x. Declares an interface function, my function, result y. Same as we do in Fortran. We bind it. We have a value coming in, and y coming returns out as well. So it's also very similar, and we call it just my function like this. And here you can see you can do this. In this case, it's actually I have a double here. And here I explicitly say that this constant here should be of the type C double. Then there will be no cost. But it kind of becomes long.
So, one question, I wonder if one can use some real defined with some precision.
Yeah.
Kind of.
You mean have real 8 or real 4 or something?
Yeah, kind defined.
That's the problem. Yeah. It probably works, but this is the way of making sure that you have the exact calling. The call is correct. But you could probably do real 8 here as well on an Intel platform. But
It depends on the way how you think. If you start off, I get given this C routine which we have upstairs, then you need to match on it, and then it definitely needs real C float here. So essentially you need to match on something which you can express in C. And I'm pretty sure that the Fortran compiler either will give you a fit if you use kind in your Fortran code. It either gives you a fit if the casting is easy or just silently cast for you.
I think if I change it to real 8, it will probably real 4, it will probably compile. But now it's depending on your platform again. So if you move it to another platform, it's not certain it will compile. If 4 is not defined as the same as C float.
I'm pretty sure it complies. It will insert casts.
Okay. Yeah.
I would assume it inserts casts.
Without a warning.
It might warn you. That was what I was saying earlier. Perhaps we can kind of play.
Yeah. So those are the things I want to show for going Fortran to C++ or C. The things that are missing, which is hard to map, is objects. So it's very hard to map a C++ object or classes to Fortran classes. Those are not kind of equivalent. So to be able to do it, you can create a Fortran class that maps the C++ methods, and you pass along the pointer for the instance. That is one way of doing it. You can do that same thing in C++ if you want to map to Fortran. You create a wrapper class that calls Fortran routines, but it has to be a function interface. You can't do export a class directly. So I have to finalize today, I have a larger example I wanted to show, but I couldn't put it in slides. So I have a CPP Fortran. So in my courses, I have,
Yeah, just curiosity. Can one use this ISO-C in Fortran 77?
Question if it becomes Fortran 77 code if you put I use ISO-C binding there.
You have to not confuse free format and fixed format. And Fortran 77, if you say Fortran 77, you are not allowed to use anything out of Fortran.
You can use fixed form.
The language, but a fixed format and free format, these are sort of different things.
But you can compile a Fortran 77 code as Fortran 90 with the use and using fixed format. But it becomes Fortran 90 then.
Yeah, you're using Fortran 90. If you prescribe with the compiler an F77 standard, so essentially English standard F77, then it should give you a fit if you
What happens when you do -77? Does it really compile Fortran 90 code anyway? It just accepts the syntax from 77.
My understanding, it should at least give you a warning or refuse to compile if it has a compiler. This is F77.
But for the C code, you could use the keyword external, which I'm not sure is part of the 77 standard, but it works.
Yeah, it's because you separately compile and you trust the linker to make the connection. Yeah. And that works. Yeah.
Yeah, but then again, it works, but if it's standard or portable, so if it breaks in the next.
Now that's
This is a major problem because most of the scientific code they live for decades.
Yeah.
So it's important to rule out all such things so it won't give a million errors the next time you run make.
Yep. And that's why you can mix Fortran 90 and Fortran 77 code, and you can wrap Fortran 77 code in Fortran 90 wrappers and make your code more robust in that way, avoiding to change a lot of things in Fortran 77 because you know it works or something. Yeah. So the final example here is an example I have for my students they do a very simple particle system. So I try to implement that particle system and integrate that into C++ code. So I have two classes that this is built upon. So I have the particle system that defines the data structures I require. So I have some properties of the particle systems, the radius of the spheres that are bouncing around. I have the positions, I have the velocities, I have the radius is stored here. I have an initialize, I have a destroy. So everything here is dynamically allocated. So this sets up the system, and this destroys the system. I can print it out, I can write sizes. So this is the kind of defines the particle system. It's a quite large class. And then I also have a class that implements the actual simulation. So it takes as input is the particle system class. It's a pointer, so it's a dynamically allocated, and I pass that over, and this simulation looks at that and works with that, and that's the simulation. So it's in it here again, we have an update for updating, we have check boundaries, check collisions, run. I also do, just for this example here, to create an interactive simulation, I have run a single iteration here, which I will call from C++ data to drive the simulation. And then you see here I have all the implementations here. So how do you get this into C++? I want to drive this simulation in a C++ application. And the C++ application in this case is a Qt application. So
now we have the opposite problem. You have a Fortran engine and want to call it C.
Yes. So I want to have a single binary that has the Fortran code built in. So it looks like something like this. So this is the user interface. I have like I said, the particles, the max radius, min radius. I can scale the visualization up and down. I can run and pause. So this is the idea. I want to create something I will live interact with the simulation. So what I did first is because I can't export these objects to C++. These are Fortran classes. So I have created a particle interface module that will contain all the subroutines that I want to communicate with from C++. In my module here, I have a private pointer to a particle system and a particle simulation. So this is the module owns two instances of these objects. I have a special interface routine here, system init, that sets up everything. We call that once. And you see, it allocates the particle system, the particle simulation, instant with the radius here coming in from the function call here. I also have a function here that can update the radius, max radius, and the velocity. And I process that along to these objects here that I have in my module. So it's no problem to have global declarations in Fortran that is not visible for C++. So Fortran can allocate them and you can reference them in the context of the C++ application. Then I also have a routine. This is probably could be done more efficiently. I have a routine here that will be called by the C++ to query the position of each particle on the radius. So basically, this just calls a routine in the particle system class to query the position of a particle. So so it has a loop because I need to draw every particle, so it doesn't matter if I call every time I want to draw. I call in here to query the position of the particle. I also have here a function for querying the number of particles in my particle system as well. And then I have here run iteration that is runs a single iteration of the system. And then I have a destroy here for destroying the objects I allocated here as well. So these are the routines I want to interface with C++. And as you can see, I have already done the bind attributes here of each of the functions. So, and also you can see here that I'm using CMake to build this stuff. So if I look at the CMake file here, hopefully you know some part of this here, but I have, in the beginning here, I tell CMake that I want to have, I need C++, C, and Fortran. I need to have C. I find out you can't just have CXX. You need to have both C++ support and C and Fortran, so that CMake activates that. In the project sources here, I just list my Fortran files here, just like normal. And then CMake will take care of building all of these, select the compiler and build those source code files depending on which, if it's a Fortran file or C++. So it's a CMake product, so it does the linking automatically. I don't have to think too much about that. What I need to do now is provide a way for C++ to see my Fortran interface. So I did a header file here called particle interface. You probably recognize this now. So I have here, I declare my routines again, those that are part of my interface module, but I declare them in C syntax now instead. So you have my init here, number of particles, rmin, rmax, speed, destroy, run iteration, system particle, and so on. So you can see I copied it in just to create these declarations. And then to integrate here, I created a special component in C++ called particle canvas. So now I hope this will be a bit C++ object orientation here, but I have a particle canvas. It has a paint event here for drawing. It has a run simulation, stop simulation for starting the loop that drives the simulation. And if I go into my canvas here, so what I do here, I create a timer object here that calls my code repeatedly. So I have a timeout here with a no parameter. That means that I want you to call this routine as fast as you can. And then I have connect this signal to a on-timer update. And what that does is call particle system run iteration and say, okay, repaint, because now I need to, after this, I need to repaint my graphics. And here I have my paint event, a lot of Qt stuff, draws the background. I query how many particles do I have. I set my colors. Here I start here. I query the Rmin and Rmax. And then I start a loop here in C++. Particle system particle. So I query my Fortran code again. I need particle, so I need to think about indexing here. C++ start at 0 in Fortran 1, so I need to update this loop to start at 1. System particle 1, and then I query X, Y, and R. I get them back here. I do some coloring here to change the colors depending on the radius. I draw an ellipse here with the parameters I get back. So basically that is the main functionality of this code. And I have my main window. And the interesting thing here is I have update controls, create particle system, and in update controls, I will query, I create particle system here. I just make sure that we're not drawing anything, so I terminate the timer. And then if this is the first time I start up, if it's not the first time, I will destroy existing particle system, init a new one with the parameters here. First time is false, so then run simulation again. So that will start the simulation and run it. So let's see what the result is here. C++ Fortran. So now I have my Qt code running, and I can scale it up and down like this. And the Fortran code is called all the time for running the application here. If there are some hints, it's probably because I'm running Zoom as well. And then you can do, let's see here, 600 and press update. And I can have more. Let's see here. And I can do larger particle sizes. But it's running the Fortran code. It's a single binary now. And it usually doesn't happen. It's that jerky now. I think it's over Zoom. So here I combined modern Qt library with my modern Fortran code. And it's a single binary. There is no shared libraries. It's one thing. And that was what I had for my first project.